Swayam Prabha. Digital India. Educated India.
Good afternoon everyone, and today we will starting with module 6 again, microtexture measurement using EBSD technique in SEM, and we will continue with the understanding of basics of electron microscopy. So, this is basics of electron microscopy part 2. So, the concepts that are covered in this lecture are the electron diffraction techniques, the formation of reciprocal lattices and how it looks like, a little bit of information about the Ewald sphere construction. So, let us start with electron diffraction. We all know that when an electromagnetic radiation is diffracted by the presence of periodic lattice arrangement in a crystal structure, what happens that if the zone axis, basically the direction at which the electromagnetic radiation is moving, if it is 100, here is the figure, then the positions of the poles, other important Miller indices pole, are positioned in such a way that they are in the surface of a sphere which is basically a stereographic sphere which is being projected in a form of a two-dimensional circle which is known as a stereographic projection, and this stereographic projection we have learned in greater detail in the previous lectures, right. And this is the 100 stereographic projection because it has 100 zone axis, and we can see that how the positions of various other 0 1 bar 0 0 1 0 0 0 1 planes are represented in poles in the circumference of this stereographic projection. But when we talk about electron diffraction, the electron diffractions, the electron beam, the energy of the electron beam depends upon the voltage. Now, in case of SEM, the usual voltage is around 15 kilovolt to 30 kilovolts, and then as the voltage between the cathode and the anode, that means the electron gun and the sample which is anode is increased, the lambda, that is the wavelength, basically decreases. So, if you look into the voltage range of the SEM, the lambda is in the range of 0.00859 nanometer. You can see that it is so less, right. And when we look into high resolution transmission electron microscope where the voltage can increase up to 200 kilovolts, we can have lambda wavelength of the electron beam to be equal to 0.00251, for example, for 200 kilovolts. So, you see that on the other hand, we have also learned that the electrons atomic scattering factor, the amplitude of atomic scattering factor given by small f, right, always decreases largely as the theta increases. On the other hand, the structure factor which depends upon the atomic scattering factor, capital F, also will decrease then as the theta, that is the scattering angle, increases, and basically in this case it will be the Bragg's principle followed scattering angle, that is the diffraction angle theta b. So, the diffraction angle if increases, then the diffracted intensity of the electron beam basically decreases largely. So, as the lambda is decreased, the theta b, that is the Bragg's angle theta, basically keeps on decreasing. That means that particular HKL plane will now diffract at a smaller Bragg angle, because the lambda has been increased, n lambda equal to 2d sin theta, right. So, the reflecting lattice planes are actually, in case of electron beam, are situated almost approximately parallel to that of the incidenting electron beam, the primary incidenting electron beam. So, you see what we can do, that as the sample, which is a very thin sample in case of TEM and which is on the holder put in a copper grade, and that sample holder or the specimen holder of the TEM is such that one can rotate and tilt that holder, you see. And when you can do that, you can bring that sample a certain important axis, say for example 100 axis, parallel to the electron beam. That means we can place the 100 plane in such a way so that its normal is basically parallel to the electron beam. And then what do you mean? That axis becomes the zone axis. So, now 100 becomes the zone axis, and we are talking about a cubic crystal where we are trying to put 100 parallel to the electron beam and making it a zone axis. And so that we can compare it with this stereographic projection here, where if 100 is the zone axis, then the positions of the smaller Miller indices 100, 110s are situated at the circumference of this sphere or the circle, right. So, if we look ahead, the diffraction pattern that can be obtained in case of electron beam striking this cubic crystal with the sample holder being rotated such that the zone axis is 100, that means that the plane, as I said 100, the perpendicular to the plane is parallel to the electron beam direction, right. So, once it is such, then you see if we have a plane which is parallel to the beam direction, that means this plane. So, the electron beam is falling along this plane, and then it will get diffracted, as because the lambda of the electron beam is so small that the theta b is so small, see, in a range of 0 to 0.15 degrees, and therefore, in a range of 10 to the power minus 2 radians. Then you see the n lambda equal to 2d sin theta could be n lambda equal to 2d theta, and this theta and lambda is so small, then the diffraction on this plane can occur in both the direction. So, it can occur in this direction and it can occur in this direction, in order to get both 010 pole and the 0 pole, and these poles will be represented here in form of reciprocal lattice, right. On the other hand, you see if we look into the other plane, say for example this plane which is 001 plane, if we look away and then if we look towards, then it is 001 bar plane, and this single plane will be diffracted in both the directions, okay, and then it will give a pole 001 and 001 bar. Like that, the diffraction can be obtained from the 01 bar 1 plane or the 011 bar plane, which is the same plane with this direction as 01 bar 1 and this direction as 011 bar, and could be represented in these positions. Like that, the other plane, right, the other plane, this one, the red colored plane with the direction this 011 and this direction 01 bar 1 bar could be represented here in form of a reciprocal lattice. So, the diffraction that is obtained from an electron gun or the electron beam looks something like this in case of a simple cubic crystal structure, and you see the diffraction spots basically corresponds to the planes of the zones that are basically, these planes are basically almost parallel, are at fully parallel actually than with respect to the incident electron beam. And you see both, for example, as I wrote here 0 0 1 0 0 1 bar, or you can say 0 1 bar 1 0 1 1 bar, spots could be indexed from the same electron beam traveling in the same direction. And basically we can do that because the electron beam is slightly convergent, very slightly it is convergent, or it is rocked, and so that both the diffraction could be obtained. And this convergence angle is the need of that convergence angles is very low, like 0.15 or less than that even, and you can see that diffraction from a single plane can take place in both the directions. So, as I was saying that lambda is so low that the theta is very low, and the Bragg's law is basically deviated because sin theta is basically equal to theta. So, n lambda equal to 2 d theta. So, theta is equal to n lambda by 2 d here. So, one can say that sin theta is equivalent to theta equal to tan theta in this case, right. So, for very thin specimen, for very thin specimen, and we know that for TEM we need very thin specimen, the diffraction also becomes relaxed, because you see the reciprocal lattice becomes elongated while the sample thins down. So, that is we will come to the next slide, but you see the diffracted spot is basically deviated through the distance which is inversely proportional to the actual distance of that interplanar spacing. What do we mean by this? We will show you in the next slide. If we look into the nature of the diffraction pattern, there are spots. So, this is 1 0 0 and this is a direct beam which is parallel to the the zone axis which was kept 1 0 0, right, and this is the distance from the 0 1 0 plane which is like that parallel to the electron beam, and the 0 1 1 plane which is parallel to the electron beam. And if you look into the spacing of the spots between 1 0 0 and 0 1 1 and 1 0 0 and 0 1 0, which is given by, you see the spacing of spot between 1 0 0 and 0 1 1 is given by 0 1 1 is given by L 0 1 1, and between 1 0 0 and 0 1 0 is given by L 0 1 0. So, L 0 1 1 is basically equal to root 2 L 0 1 0, and we can see it from the figure. But if we look into the actual crystal arrangement for this cubic unit cell, you will find out that the crystal arrangement, and you are looking around, you see again in the axis 1 0 0, where the plane, this plane along with the screen is 1 0 0, and on which the atoms are arranged like this in periodic fashion at equal distance. So, if these planes are 0 1 0 planes and the perpendicular to this plane, the direction is 0 1 0, right. So, the distance between these planes, that is d 0 1 0, is given, and this is this much. We look in the same plane, if we call it a plane, this plane 0 1 0, the direction along the vertical is 0 0 1, right. On the other hand, if we are looking into this particular plane which is 0 1 bar 1, this is also 0 1 bar 1, and the direction to this is 0 1 1, the same direction, then the distance between this 0 1 bar 1 plane is given by this particular d, right. Now, if we compare this distance with this distance, then d 0 1 bar becomes equal to 1 by root 2 d 010, right, whereas this is in the real lattice space. And what happens that L 011 equal to root 2 L 010 in the reciprocal lattice space. So, the distance of the spots of the reciprocal lattice space is inversely proportional to the distance of the planes in the real lattice space, right. And the spots in the reciprocal lattice space are basically the planes only. So, you can see that the spacing of the spot in the diffraction is inversely proportional to the lattice interplanar spacing, right, not the lattice spacing, interplanar spacing. So, actually this is in very good agreement with the Bragg's law. Why it is so? Because you see theta is equal to n lambda by 2 d for that HKL plane, and what is theta? Theta is basically the distance between the two spots from the center spot to this spot, right. So, as the d HKL is increasing, then the theta is decreasing, or the d HKL is decreasing, then the theta is increasing, vice versa. So, this reciprocal lattice spacing actually is in good agreement with the Bragg's law with respect to the interplanar spacing for the real lattice case. So, we can tell here that reciprocal lattice of face centered cubic material looks like BCC, whereas the reciprocal lattice of body centered cubic material looks like FCC, face centered cubic. And this is basically the way while crystallographers understand that what is the basic lattice structure by observing the reciprocal lattice of a certain unknown element. So, we get the information about the crystal structure, we can get the information of the internal defect structure of the material at the same time using this technique. So, what we do in electron transmission electron microscopy in order to get this kind of diffraction is that we use a diaphragm in the electron beam path, and the diaphragm has a very small radius about 0.5 micrometer, and it helps us, it makes it possible to obtain information from a very small area of the specimen, a particular position where it is a single crystal in the polycrystalline specimen, and therefore, this kind of diffraction pattern are called as selected area diffraction pattern. Okay. So, thinking that what you should know about while we are doing this course. So, we should have an understanding of the Loy's equation of diffraction, which is basically equivalent to the Bragg's law, because it is important for electron diffraction. The second thing and the most important thing is to understand the Ewald sphere construction. And you see that what is an Ewald sphere? An Ewald sphere is a sphere where the lattice, reciprocal lattice spots or the poles should interact in order to get the diffraction. And you see, when while doing transmission electron microscopy, if the specimen is made thinner and thinner, the crystal in it may deviate the Bragg's condition and it will yet diffract. And why it is so? Because as it is becoming thinner and thinner, the reciprocal points or the reciprocal spots or the reciprocal poles of those HKL planes it gets extended in the direction normal to the plane of the specimen, or it gets extended along the direction parallel to the electron beam, and then it more likely to get intersected by the Ewald sphere. So, as the specimen gets thin, the chances that the Ewald sphere touches these reciprocal lattice poles, which are now looking like rods, long rods, and therefore, it gives the diffraction, right, in a thin specimen in a more proper manner. So, you see the LR is the length of those rods or the lengthened reciprocal lattice spots. Lengthening is along, elongation is along, perpendicular to the plane of the specimen or along the electron beam, is basically inversely proportional to the specimen thickness. So, on the other hand, so we can get a spot which looks like this, and we can get a large amount of spot from which we can observe that what crystal structure it is, at what zone axis we can rotate the specimen holder and put it in a certain zone axis and observe the diffraction spot and find out information about it, like whether the material is nanocrystalline or it is larger grains, or it has some deviation in the crystal structure, like that. But you see, as on the other hand, as the crystal thickness is increased, so while the crystal thickness is increased, the background diffusion of the pattern starts to increase. So, you see, this is for the thinnest specimen, and then the specimen thickness is slightly more, and you see there is a background diffusion. You see it has become, the beams have become slightly spread out, right, and there are slight diffusion also in between them. Now, with the further increase in the thickness of the more, this kind of diffusion will take place. Now, why this kind of diffusion in the spot patterns are taking place? Because you see, the thicker the specimen, the number of times the scattering is taking place between the incident electron beam and the electrons and the electron cloud present in this specimen will keeps on increasing. So, if the specimen is thin, then the scattering is mostly elastic with no detectable loss of energy, while the specimen is getting thicker and thicker, the the electron beam is scattering several times, and then it will get, there will be a loss of energy, a detectable amount of energy is lost, and then it becomes multiple scattering or inelastic scattering. So, finally, you see, when the thickness is large, this type of spots, they starts to form like slight diffused kind of bands could be observed. You see, in this case also diffused kind of bands could be observed, and this happens because when multiple scattered electron, multiple times scattered electron, or inelastically scattered electron finally scatter one single time before leaving the specimen, and that scatter should follow the Bragg's law or the Loy's equation, so that it diffracts at that particular angle as per the Loy's equation or the Bragg's law, so that it can be said diffraction. Then it will form, subsequently it will form a Kikuchi pattern, which is like a band or a line instead of spots. So, you see, these bands that are forming, they are basically formation of Kikuchi pattern, which can be observed when the samples get thicken and thicken in a TEM. So, what we can conclude? So, the conclusions are, in the electron microscope, as the voltage is increasing, the lambda is decreasing, right, and as the lambda is decreasing, the theta following Loy's equation or the Bragg's law is decreasing. Simple as it is, the Bragg's law becomes relaxed. The diffracted spots will be deviated through the distance that are inversely proportional to the interplanar spacing of that particular crystal structure. So, Reciprocal lattice of face centered cubic is basically body centered cubic, and body centered cubic looks like face centered cubic. This is also a thumb rule. So, a diaphragm is kept in between the specimen and the electron beam, so that it can irradiate only a small area, say 0.5 micron, and then one can get a selected area diffraction and the diffraction spot. So, thinner the specimen, you see the reciprocal, as I said, the Bragg's law is relaxed and the reciprocal spots becomes increasingly elongated parallel to the electron beam or perpendicular to the sphere, touches very easily that elongated reciprocal poles, and thus even though the crystal may deviate from the Bragg's condition or the Loy's equation condition, it will yet diffract. Lastly, as the sample thickness increases, some multiple scattering or inelastic scattering will take place. Subsequently, there will be final elastic scattering, where the scattering takes place following Bragg's law, and it comes out of the sample forming band type of structure instead of spot, which is known as Kikuchi bands or Kikuchi patterns. We should remember here that when Kikuchi pattern we are talking about, the electron beam is falling, it is not only diffracting from a single HKL plane to form Kikuchi pattern, it will be diffracting from a multiple planes, to form bands which are intersecting each other. We will talk about this later. That means several HKL planes are being diffracted to form several Kikuchi bands, leading to form multiple Kikuchi bands in a phosphor screen, and that is what we call it a Kikuchi pattern. Thank you very much.